Okay. All right, let's go and quiet down, please. Let's go and get started. Okay. So a couple of quick announcements. Quiz 2 is today at the end of lecture, covering lessons 1A and 1B. Quiz 3 is going to be next Wednesday, covering lessons 2 and 3. So last Wednesday's lecture and then today's lecture. So before we get started, any quick questions on anything that stuck out the homework? All right, cool. So let's go ahead and look at lesson 3 real quick. So basically this is lesson 3, substitution with a natural log. So nothing much new today, except we're just doing more substitution with a slightly different integral. Okay. So let's start with some definitions. So the inverse of the exponential e to the x is f inverse of x equals natural log of x. Okay. So you guys probably already knew that, but just a quick little review on that. And some important properties are given below. So we have natural log of e to the x equals x, and e to the natural log of x equals x. Okay, so these two properties just follow from the fact that e to the x and natural log of x are inverses of each other. That's all it says. Okay. So just as an example, natural log of e cubed equals 3, and e to the natural log of 2.6 equals 2.6. So that's all that means. And on a similar note, we also have that if we have natural log of x equals y, then that's equivalent to e to the y equals x. Are equivalents. Okay. The C property is domain of the natural log of x is 0 to infinity, or x is greater than 0. So whatever's in here has to be positive, basically. And the range of natural log of x is negative to positive infinity. Property E states that the natural log of a to the power of b equals b times natural log of a. Property F, natural log of a times b equals natural log of a plus natural log b. G, natural log of a divided by b equals natural log of a minus natural log of b. And then the integral of 1 over x dx equals, bless you, natural log of the, remember, it's not just natural log of x, it will be natural log of the absolute value of x plus c. And then the last one is that the derivative of natural log of x is just 1 over x. Okay. Alright, so now that's quite a bit that I wrote down, so I'll give you guys a second to write all that. So mostly this is just review stuff, so there's just some nice properties that it would be good to know for natural log stuff. So that's that. So in terms of this class, though, I think some of the most important ones are definitely these for sure. And then let's see. I think this one probably important as well. Yeah, this definitely these three. But the other ones are mostly just a review that you should already know about the properties. Okay. Though I think E through G will be important if if they're in a multiple choice situation on an exam and they're like, okay, well, if you have something in exact value form regarding natural log, and they have something simplified, then what would the answer be in that? And I'll briefly touch one of these in the first example, but yeah. Okay, So I'll give you guys a second to write all those down, and then we'll go ahead and move on to the first example. Okay. So give you guys about 15 more seconds or so, and then we'll move on. Alright, so let's move on to example 1 then. So, the premise is we have to evaluate this integral rounded to 4 decimal places. Okay? So we have the integral from 0 to pi over 20 of 5 times secant squared of 5x over 3 plus tangent of 5x dx. Okay? So, noting the title of today's lesson is that we have to utilize substitution methods with natural log now. So, in some sense, you can think of this as substitution lesson 4. Yeah, studying 4 lessons on one integration technique. So, yeah. Anyways, so let's take a look at that, shall we? So, what would be the good u substitution that we should employ here? We could do that. So if you want to do 5x, that means du would equal 5 times dx. And then as a result, you then see, all right, well, we have that, we're going from x equals pi over 20 and x equals 0. So if we do that, we then say, all right, well, we have, if x equals 0, pi over 20, that means u would have to equal what? Just pi over 4, right? And then similarly, if x equals 0, well, this will give you that u should equal 0 as well. Okay? And then since, if we solve for dx here, we get du over 5. We can then get, all right, the integral from 0 to pi over 4 of essentially 5 times secant squared of u over 3 plus tangent of u, and then du over 5. So then these 5's cancel each other out. So ultimately, we're just left with the integral from 0 to pi over 4 of secant squared of u over 3 plus tangent of u du. Okay? But then, all right, well, wait a minute. How do we solve this thing? So, take a look at that. That probably means we need another u substitution. So, what do you think would be a good one here to utilize? Yeah. What was it? Right idea, but I would go a bit further. I would add the plus 3 as well. So in this case, I'm going to call this one v equals 3 plus tangent of u. Okay? So then that way we can say, all right, well, dv then equals what?
Secant squared u.
Yep, secant squared of u times du. Okay, and then so from here we can change the bounds as well, right? So in this case, if we have u equals 0 and u equals pi over 4, that means that v, what would be the corresponding v values? So if we let u equals 0 in here, then we should get that v equals what? So if we harken back to our unit circles, so first off, what is tangent of 0? What's that? It's just 0, right? So that means you essentially have 3 plus 0, so 3. And then if u equals pi over 4, then what would be tangent of pi over 4, if you recall from the unit circle? So what is tangent of pi over 4? is 1, right? So add that to 3, and then you end up with uv equals 4. Okay? So in this case, we then have that the lower bound becomes 3, the upper bound becomes 4, and then so you realize, so we have secant squared of u over, in this case, v, times dv over secant squared of u. If we just note that, if we just solve for du here, then we end up with du over secant squared of u equals d. Now, sorry, dv over secant squared of u equals du. Okay? Okay? So then these secant squareds go away, and ultimately we're just left with the integral from 3 to 4 of dv over v. Okay? But then you realize, well, wait a minute. I already know what the antiderivative of, well, 1 over v is with respect to v, right? If we look back up here, that's just the natural log of the absolute value v, going from 3 to 4. Right? So then if we apply the fundamental theorem of calculus from this, we then say, all right, well, we have natural log of, in this case, 4 minus natural log of 3. Okay? So in this case, as an exact value, this is one correct way to represent it, but let's say, for the sake of hypothesis, or for the sake of hypotheticals rather, that this were not an explicit choice on the exam. So looking back up here at property G, we note that this expression here, down the bottom, can be rewritten as, using property G, we can rewrite this as, well, natural log of 4 over 3, right? So in terms of exact values, this could be another way to represent your answer. Okay. So there's that. And then so if you put this into a calculator, you should be able to pretty quickly get 0.2877. Okay? All right, and that's example 1. So any questions on that one? Yeah?
Did we have to start with using, or substituting 5x? Like, could we have just chosen 3 plus 10 and 5x to begin with?
You could do that as well. I answered it this way just to break things up a bit more, but if you want to start with u equals this whole denominator here, just to save on a bit of time, you can do that as well. Okay? Yeah?
So if you keep like substituting different values, can you go like, is there a limit to how much you can do that, or is it just? So like you did u and then you did v, like could you keep going after that, or is there like a limit?
Well, the only reason I stopped at v is because we know the antiderivative of 1 over v, right?
Yeah.
So in this case, you only really need to do it twice, but it kind of just depends on how you utilize your substitutions, basically. Okay. Any other questions? Okay. So let's move on to example 2 then. So moving on to example 2. So in this case, we have evaluate natural log of 3x to the 5th quantity squared over 5x. Okay? So in this case, it looks like we're going to need to utilize another u substitution. So in this case, what would you want to let u equal here? Any thoughts or suggestions? We could do that, but here's the catch though. We don't really know, if we look at just 3x to the 5th, there's not really a good, it doesn't really look like there's a constant multiple of, in this case, x to the 4th in our integral, right? So let's try looking at something else. So we know that if we look back at some of the properties of natural logarithms, we know that the derivative of natural log of x is 1 over x, right? So taking that into account, what would be another thought about utilizing a u substitution? What else would you want to try? Yeah. Not quite. Well, remember, trying to take whatever our u substitution is, we need to have its derivative be a constant multiple of something else. So in this case, let's try, well, we have natural log of x in our integral somewhere, and we have its derivative as a is a constant multiple of something else in our integral, right? So yep, so in this case, you would probably want to let natural log of 3x to the 5th be your u substitution, right? because we have natural log of something, and what you also notice is that if you take the derivative of this thing with respect to x, then what do you end up with? Yeah, so, well, that's part of it. So remember, 1 over 3x to the fifth, because you have to take 1 over whatever is in here, but then by chain rule, we have to multiply that by what? 15x to the fourth. Good. And then dx. And then you realize, well, wait a minute. This simplifies pretty nicely to just 5 over x, doesn't it? So then what you can do from that is say, all right, well, so now du equals this thing. So if I solve for dx from this, then I should be able to get dx equals x over 5 du. Okay? So in general, if you have something like, something natural log to some to some power over x, then that should be a pretty good indication that you need to let u equal natural log of whatever. That's usually your best bet in that case. Okay? At least if you have a polynomial here somewhere. But if natural log of some polynomial. Okay? Alright. So, taking that into account, we have, well, u squared, because natural log of 2x to the fifth is u, over 5x. And then times dx, which is x over 5 du. So then you note, all right, well, x's cancel each other out. And we're just left with u squared over, in this case, 25, because of the 2 5 factors down here. Okay. So that has a pretty nice antiderivative of what? So what is the antiderivative of u squared over 25?
Is it 1 over 75 u to the third?
Yep. It would be u cubed over 75.
Plus c.
Yep. Make sure to remember plus c, because remember, you will need that on the quiz, so make sure not to forget plus c. You will lose points for that. Okay? So, and then noting that we have to make sure everything is back in terms of our original variable, then we have that our final answer must then be natural log of 3x to the fifth cubed over 75 plus c. Okay? All right. So, any questions on any of that? Okay. So, good, nay, somewhere in between? Cool. I'm seeing a lot of thumbs up. I like that. Okay. So, moving on to example 3. So, the third example says, suppose a hot air balloon is deflating in such a way that its volume changes at the rate of v prime equals 2 over the cube root of t times t to the 2/3 minus 25 meters cubed per minute, with t in between 0 and 120. If the volume before it starts deflating is 15,000 cubic meters, we need to find the volume 1 hour later. And we need to round to 3 decimal places. Okay? So here we have, v prime of t equals this function here. And we also have a piece of data here, right? So if v of t equals the volume function at time t, then the problem says that the volume before it starts deflating is 15,000. So, as per what we have seen enough times at this point, that says that v of what equals what? So, yeah, so v of 0 equals 15,000. Okay? So that gives us that, and then that tells us this is all we're given. And we need to find the volume 1 hour later. Okay? So that means we need to find v at what time? Someone else? Careful. 60, right. So again, this is where we need to be careful of our units here, because the volume is the rate of rate of change of volume is given in meters cubed per minute. So that should be a good enough indication that T here is in minutes. Okay? So T is in between 0 minutes to 120 minutes. So since 1 hour equals 60 minutes, we got to find V of 60 here. Okay? So that gives us that, and then round 3 decimal places, but we'll get to that later. So if you recall, from the last 2 lessons that we've been seeing, there's a way to figure out the numeric value of this guy given the rate of change of volume as well as the initial condition. So do you guys remember how we did that using fundamental theorem of calculus?
First you take the antiderivative with no bounds, and then you solve for C and then take it with the bounds.
Well, you could do that. So that's basically finding the particular solution and then working from that.
Oh, yeah.
But there's another way of doing it using the fundamental theorem of calculus, so i.e. using definite integrals as opposed to indefinite integrals. Yeah?
V of 0 plus the integral from 0 to 60, right?
All right. So remember, the fundamental theorem of calculus says that if we take this difference here, then the fundamental theorem of calculus states that this difference here can be represented as the integral from 0 to 60 of v prime of t, which corresponds directly to this guy. So we have 2 over cube root of t times t to the 2/3 minus 25 dt. Okay? So that says, okay, well, we already have v of 0, because that's right here. So once we evaluate this integral, we can just add v of 0 to the other side, and then we're done. Okay? So let's first start by evaluating this integral, and then we'll go from there. Okay? So, since we're still in substitution land, what would be a good u substitution to work with here? Based off of what you are seeing in this integral.
T to the 2/3 minus 25.
Yep. T to the 2/3 minus 25, right? Because what you notice is that if you take its derivative, then you should end up with what?
What is it?
Yep. Yeah, so you will need 1 over the cube root of t and then dt, but what's the constant that's multiplied by that? What does the derivative power rule say about that?
That's 2/3 minus 1 over
Yep, it's 2/3, right? Okay. Okay, so then that would imply that if you solve for dt here, then you should be able to see that this is just equal to 3 times the cube root of t over 2 du. Okay? Okay? So then as a result of this, we can then say, all right, we can also change the bounds as well. So we can have t equals 60 and t equals 0. So if we change these bounds here, then we get the corresponding u values as what? So if t equals 0, then what would the corresponding u value be? Yep, negative 25. And then similarly, if t equals 60, then you just let t equals 60 here to get 60 to the 2/3 minus 25. Now, in terms of exact values, this upper bound here is the best you can do. So we'll just leave it as is, and then we'll go from there. Okay? So what happens? So we have negative 25 to 60 to the 2/3 minus 25. So let me zoom in a bit on that. There we go. So 60 to the 2/3 minus 25. So that would be 2 over cube root of t times u, and times dt, which is 3 times cube root of t over 2 du. Okay. So then you notice, all right, the cube root of t's go away, and so do these 2's here. So ultimately, your definite integral becomes negative 25 to 60 to the 2/3 minus 25 of 2 over u du. Okay? Okay? So then from here, we can say, all right, well, oh wait, sorry, this would be 3, my bad. The 2's cancel each other out, so all we're left is 3. Sorry, my bad. But in any case, what would the antiderivative of 3 over u be?
3 natural log u.
Careful. Absolute value, right. In this case, we actually do need the absolute value here, and you'll see why in a second. So here's our bounds. So then if we apply the fundamental theorem of calculus, then what you notice is that this is 3 times natural log of the absolute value of 60 to the 2/3 minus 25, then minus 3 times natural log of the absolute value of negative 25. Now you see why we need the absolute value here, right? Because now, as we established in page 1, the natural log, the domain of natural log is normally all positive numbers, right? So if we forgot this absolute value, then we would try to be taking the natural log of negative 25, which does not exist. It's undefined, because the domain is all positive values. So thankfully, this absolute value here fixes that issue. So that's why we need absolute value here. So now that we have the value of this definite integral, that then says, okay, at the end of the day, that means v of 60, if we add v of 0 to the other side of this exact value we then have v of 0 plus, well, all this. Okay. So as an exact value, well, this equals, well, v of 0 was 15,000 as we established. So 15,000 plus 3 times natural log of 60 to the 2/3 minus 25. And then minus 3 times natural log of, in this case, just 25. Since the absolute value gets rid of our negative here. Okay? So then put all this into a calculator, and then you should end up with 14,997.152. Okay? And if you take a look at the units in the problem, then what should that indicate about the units that we need to have in our final answer? So if v prime of t is in cubic meters per minute, then what should that tell you about the volume that we need to have at the end of the day? It needs to be in units of what? Yeah, cubic meters, right? Okay. And that is example 3. So, any questions on any of that? All right. Okay. Cool. So, let's go on to the last example. So, sort of a continuation from example 4, or example 3 rather. Thankfully, the person driving the hot air balloon notices a balloon deflating and so descends the balloon in a way modeled by h of t equals 180 over 3t minus 100 meters, with t between 60 and 120 minutes. And the goal is we need to find the average, oh gosh, that was terrible, the average height of this balloon over the interval. Okay? So, if you take this keyword average into account, then that means we need to use that average value formula that we talked about last time, right? So, in this case, we're saying, all right, we need to find the average value of this height, which is modeled by h of t equals 180 over 3t minus 100. And thankfully, they also give us the interval explicitly over 60 and then a comma 120. Okay? So, taking that into account, that means if we harken back to our average value formula that we talked about last time, do you guys remember what that states? So what would that give us here? So what was the average value formula here?
The antiderivative of h of t over b minus x.
Mm-hmm. So well, not just the antiderivative, but we need the definite integral, right?
Yeah.
So in this case, we have when the lower bound is 60, the upper is 120, and then we need the length of our integral, which is 120 minus 60, right? Okay? So here's what that tells us. So we have, okay, so in this case, this is something over 120 minus 60, which is, well, that's clearly just 1 over 60. Okay? So it's 1 over 60 times integral from 60 to 120 of h of t, which we explicitly established as 180 over 3t minus 100. So 180 over 3t minus 100 dt. Okay? So here's what you notice. So if we put this 1 over 60 into our integral, then you notice some things cancel out, right? So we have 60 to 120 of 1 over 60 times 180 over 3t minus 100 dt. So how does this simplify? If we bring this 1 over 60 into our integral, what cancels out? Oh, what was that? Yeah, because what you notice is that 1 over 80 divided by 60, well, that's just 3, isn't it? So we ultimately have 60 to 120 of 3 over 3t minus 100 dt. Okay? So then, what would our u substitution that we should utilize be here? So raise your hand if you have what the, yeah? Yep. Let u equal 3t minus 100, right? Because then, well, du, well, you should be able to see pretty quickly that that's just 3 dt. And then so that's that part. And then so you should be able to get pretty quickly that if you solve for dt, that's just du over 3. Okay? And then because this is a definite integral, we also have to correspondingly change the bounds, right? So in this case, if u equals, sorry, not u, not yet anyway. So if t equals 120 and 60, so if t equals 60, then what would our corresponding u value be? It's just 80, right? And similarly, if t equals 120, then what would its corresponding u value be? Yeah, it's 260, right? Good. Okay. So then correspondingly, that gives us the integral from 80 to 260. Let's see. So we have 3 over, in this case, just u, times dt, which is du over 3. So that's the integral from 80 to 260 of, well, these 3's pretty nicely cancel each other out. So we're just left with 1 over u du. Okay? So, as we've already seen, well, that has antiderivative of what? Good, remember the absolute value. So natural log of the absolute value of u from 80 to 260. Okay? So then if we apply the fundamental theorem, then as we've already seen, well, by similar reasoning as to what we've already seen, this is just natural log of 260 minus natural log of 80. Okay? So, again, this is one way to express the exact value, but let's say, again, we were not given this choice on an exam. So, instead, if we had, something that's just natural log of just one thing, then using log properties, what would that something in here be? Good. 260 over 80. Good, 260 over 80. Okay. And then from here you would simplify as necessary. So that would be, I think, yeah. So if we simplify the fraction of this, what would that be? Go. Yeah, it's 13 over 4, right? Okay. So then if you plug this into your calculator, then you should get, if you round to 3 decimal places, 1.179 meters. Okay? And that is example 4. And just as a quick little remark, you notice, well, that's not really a big height. That's only like 1 meter above the ground. Well, as my little remark on the start of the problem put, it's a starting business. That's the excuse. So, yeah. In any case, that's example 4. Any questions? Yay, nay, somewhere in between? Cool, I see 2 thumbs up. I like that. Okay. So in that case, let's go ahead and get ready for the quiz. And make sure you have a one-line calculator. Okay. All right. You guys have until the end of class to do this quiz. So, good luck. Just so you guys know, it's currently 12:08, so you guys have a couple extra minutes to do the quiz.